In 1961, this paper divided the whole statistics community. Prior to that, a very influential statistician, Ronald Fisher, popularized a theory called maximum likelihood estimation, which is regarded very, very highly. But this paper challenged their firm beliefs, so it was such a shock that the result is now known as Stein's paradox. Let's see what this is about. Suppose I have a set of data that follows a normal distribution with some unknown mean mu and a variance of 1. Now I randomly pick a sample, a data point from this distribution, and let's say I picked 3.14. Your job is to estimate the value of mu. What would you estimate? On screen, it looks like it is slightly more than 3.14, but the point is that you don't know the value of mu. It could also be on the left of 3.14. The only thing you know for sure is that data point 3.14. So without much more information, you might just estimate mu to be 3.14. That's a sensible guess. After all, a normal distribution is clustered around its mean mu, so there is a good chance that the 3.14 picked is in the proximity of mu, and the error of your estimate would not be too big. In theory, that is the best estimator, in some sense of the word best. Now we play the same game, except this time we have two sets of data. They are completely unrelated to each other, but they both follow normal distribution with means mu1 and mu2, both variance 1. Again, I picked one data point from each of the distributions, and let's say they are 3.14 and 1.618. Now what would you estimate? By exactly the same logic, you might also estimate mu1 to be 3.14 and mu2 to be 1.618, and again, this is the best estimator in this situation. But things change if we have three independent sets of data. Exactly the same setup, normal distribution with unknown means and variance 1. Normally, if I have the data points x1, x2, and x3 respectively, then you would again estimate mu1 to be x1 and so on, just like the previous cases. But now this is not the best estimator anymore, because in 1961 we found a better one called the James-Stein estimator. If the data points are x1, x2, and x3, then this is the James-Stein estimator of the means. So in order to estimate mu1, it is better to multiply this factor in front rather than simply saying x1. This is really surprising. Those three sets of data are completely independent from each other, but in order to estimate mu1, it is better to incorporate all three data points because the prefactor depends on all of x1, x2, and x3. This surprising result is now known as Stein's paradox. But this is not the only surprise here. James-Stein estimator generalizes to p sets of data, where p is at least 3, and very similarly, the estimate is going to have this factor in front. So our ordinary estimate, which is just echoing back the data points x1 up to xp, was the best in 1 and 2 dimensions, but is overpowered by the James-Stein estimator in 3 dimensions and above. What happened there? What's more, that really trusted theory of maximum likelihood estimation also supports our intuition. The theory also tells us to just use the data points given, the ordinary estimator. So the fact that the James-Stein estimator beats a well-studied theory definitely caused chaos in the statistics community. But what do I really mean by an estimator being the best? To quantify how good an estimator is, we use the mean squared error. Error is the difference between our estimator mu hat and the true but unknown mean mu, and then we square it to make it positive. In the case of multiple sets of data, we treat those estimators and means as vectors and consider the norm of it squared. In other words, we just consider the squared error in each component, then add them all up. Finally, we take the average. This is taken to account for the randomness in the estimator. To be clear, if we see a certain sample X, it already determines our estimate mu hat. You can't introduce your own bias here. So this process is entirely deterministic, not random, but the samples taken are random because they are taken from a distribution. So the expected value here takes all possible values of the sample into account. In other words, this is how much, on average, the estimator deviates from the true value. For example, in the one-dimensional case, what is the mean squared error of the ordinary estimator? The estimator is exactly the sample taken, so if we have the sample being x, then the estimator will be x. In this case, the mean squared error turns out to be the formula for the variance of x. We have assumed that the normal distribution has variance 1, so the mean squared error is 1 in this case. But the error in general depends on mu, the true mean. To illustrate this, let's take a naive estimator 7. Whatever sample I have taken, you are just going to estimate the mean to be 7 anyway. The mean squared error is then the expected value of 7 minus mu whole squared. However, the square inside does not depend on the sample x, and so it is not a random quantity. Therefore, the expected value is just what's inside, 7 minus mu whole squared. This clearly depends on the true mean mu. We can then plot the mean squared error of these two estimators against the true mean mu. The ordinary estimator returns a constant 1, independent of mu, and the naive guess 7 is a parabola, centered around mu equals 7. In this case, we can't say definitively which estimator is better, because if the true mean is actually close to 7, then the naive estimator 7 will, on average, perform better than the sensible ordinary estimator, i.e., it has lower mean squared error. But of course, for the other ranges, the ordinary estimator performs better. So now, let's say that one estimator A has the mean squared error consistently below another estimator B. Then we say A dominates B. We call the ordinary estimator the best estimator in the sense that no estimator can dominate it. So this blue graph entirely below the ordinary estimator will not happen. Sure, some regions can be outperformed, like near 7 for the naive estimator, but not the full parameter space. More professionally, if this will not happen to any other estimator, such an estimator is called admissible. So the ordinary estimator is admissible in this case. In higher dimensions, our ordinary estimator would have the squared error being the sum of the individual components, so we just add those means up. If we have p sets of data, because the mean squared error of individual estimates would be 1, the sum would be p, independent of the true means mu1 up to mu p. So again, if we plot the mean squared error, it will appear as a straight line. However, this is the graph of the James Stein estimator, which is demonstrably below the red line. In other words, the James Stein estimator dominates the ordinary estimator. This is only the case for p equals 3. For other values of p, we scale the graph appropriately, but we can see that the James Stein estimator has much better performance than our ordinary estimator, especially when the means are close to 0. But why does the James Stein estimator perform better? If you want a more rigorous explanation, including where exactly the divide on dimensions takes place, I have made another video on the second channel. I'm not doing it here because it feels more like manipulating symbols, not shedding a lot of light on the more general lessons learned. But before I talk about the intuitive explanation, I want to give thanks to this video sponsor, NordVPN. Early on, I traveled to Iceland, and it is certainly a very unique and beautiful country. But whenever you use a public Wi-Fi, such as airport Wi-Fi, hackers can see your personal information if you are careless and go to a website without the HTTPS protocol. A VPN creates an encrypted tunnel that can make sure your personal information is safe. Also, any website can track your IP address and know where you are. Using a VPN means that those websites cannot easily track you. I originally thought that since a VPN adds an extra layer of encryption, it will slow down your connection, but was surprised to see that there is virtually no difference in internet speed before and after using a VPN. You can now go to nordvpn.com/mathmaniac to get a 2-year plan with an exclusive deal, plus 4 bonus months free. It's risk-free with NordVPN's 30-day money-back guarantee, and you can also support this channel by signing up. Alright, let's go to the intuitive explanation for why the shrinkage factor works. If we look at the form of the James Stein estimator, there is this factor here, which is usually called the shrinkage factor because normally this factor is between 0 and 1. However, if the data points are too small, then the denominator can be very small, and this will make the supposed shrinkage factor actually negative. Even with this flaw, the James Stein estimator still performs better. Geometrically, in the two-dimensional case, we can plot the true means μ1 and μ2 as a point on the 2D plane. Variance 1 means that the data is roughly distributed like such, circularly symmetric around a red dot. The mean squared error incurred would then be first taking the distance of the sample to the red dot, square it, and then repeat this action of squaring distance to take the average. Here is how the shrinkage factor might minimize the average. For points further away from the origin, by making it closer to the origin, you also move closer to the red dot. The drawback is, of course, for points already close to the origin, the shrinkage factor will get it even closer and further away from our red dot. Fortunately, only the points in this finite circular region will move further away from the red dot by shrinking towards the origin. For all the other points, you get closer to the red dot by shrinking towards the origin. Yes, that even includes the points on the left of the axis. So overall, we might get a reduction in distance towards the red dot. Let's call this blue region the far end and the green region the near end. The trouble is, what if shrinkage only gives a tiny reduction on the far end, but a considerable enlargement on the near end? Then the advantage gained by having a larger area of reduction is diminished. Unfortunately, this is sort of what happens for the James Stein estimator. When we compute the distance from the James Stein estimator to the origin, we will have this shrinkage factor, as usual, times the original distance from the origin. So the absolute reduction in distance is this extra term, which can be simplified as such. Notice that the original distance is in the denominator, which means that if the original distance is large, i.e. further away from the origin, then this reduction in distance is smaller. This is the kind of stuff that we don't want to see because it precisely means that on the far end, where the original distance from the origin is normally large, gets a smaller reduction towards the red dot, and those on the near end gets larger addition in distance from the red dot. So there is always a tension between a much larger area for potential reduction in distance versus the smaller actual distance reduction. This is where dimensions come in. In 3 dimensions, for instance, we can similarly plot the true means as a point, and similarly, we can define the near end and the far end. In higher dimensions, there is just more stuff out there, so the effect of a larger volume is much more pronounced, which makes this method of shrinkage really work in higher dimensions. This is already quite an important lesson in modern statistics, but there is an even more general concept at play. Let's revisit the formula for the mean squared error. We have the expected value of something squared, which might remind you of the formula for variance. Now we can simply rearrange this formula and substitute that x to be mu hat minus mu. Then we will get a formula that decomposes the mean squared error into 2 parts. Because mu is a constant, not random, the variance is the same as just the variance of mu hat. And the expected value of mu hat minus mu is called the bias. In words, the mean squared error is the sum of variance and bias squared. But what does that mean? Pictorially, let's say the true mean mu is represented by the vertical line here. Remember that an estimator is random because it depends on the samples, so it has a distribution, such as this one on screen. This depicts the situation where the mean of this distribution mu hat is exactly mu, the thing we are trying to estimate, i.e., the bias is 0. However, its variance is quite large, so if we perform the estimation, it is very possible to be far away from mu, and the error is quite large. Sometimes it might actually be better to introduce a little bias if the variance could be dramatically reduced. Then most of the time, it just could not go too far away from mu, and the overall mean squared error remains small. This is known as bias-variance trade-off, the idea that the mean squared error, in some cases, could be reduced by increasing the bias slightly if it means that the variance can be reduced by a lot. This is very well illustrated by the James Stein estimator. The ordinary estimator just directly copies the data points. There will be no bias in this estimation. But during the shrinkage process, clearly the center of all these points is not exactly the red dot, so this is clearly biased. However, the points are significantly closer together than without shrinking, reducing variance. Sure, an unbiased estimator like the ordinary estimator has some beautiful symmetry in it, but it could perform worse than a biased estimator that has a much lower variance. Perhaps you might be thinking that this is only a simple toy problem, which it is, but the lessons about shrinkage and bias-variance trade-off are hugely important in modern statistics. Nowadays, a lot of times, we are dealing with a real-world situation where there are some inputs and outputs, and we are trying to imitate it with a mathematical model. Normally, our model might have a lot of parameters, which you can think of as adding different weights to the inputs. But then, because we don't expect the real-world situation to be that mathematical, if there is any difference between the model prediction and the real-world situation, we say it is just due to random noise. Then, based on observing a lot of sample input-output pairs in the real-world situation, we try to estimate and fine-tune those parameters or weights so that we can use less noise term to explain away any disparity. Compare this to the estimation problem that started this video. Again, we try to observe some sample from the distribution and we try to estimate the underlying parameters, the means mu1, mu2, and so on. What James Stein estimator illustrates is that if there are many parameters we need to estimate, the shrinkage factor could really reduce the mean squared error, and much more dramatically when the number of parameters becomes larger and larger. The growing number of parameters is exactly the situation in this century. For more complicated models, shrinkage can even help us decide which inputs are actually important and which aren't, especially if we shrink some of the weights all the way to 0. This idea of shrinkage is known as regularization in the world of machine learning. Of course, we might not use James Stein estimator directly in the real-world situations, but the lessons of shrinkage and bias variance trade-off continue to be applied in modern-day statistics. In fact, there are way more things that we could say about Stein's paradox. For instance, James Stein estimator is not even admissible either, i.e., there are some other estimators that dominate it. I will leave those in the description below. Thanks again to the patrons. Subscribe with notifications on, like, share, and comment as well. See you next time.